Welcome to another edition of RCE. Again, this is Brock Palen. You can find us online at rce-cast.com. You can find links to Jeff's the blogs, the Twitters, and all that other fun stuff. Also, I have again with me Jeff Squyres from Cisco Systems and one of the authors of OpenMPI. Jeff.
Hey, folks. Yeah, it's that traditional post-SC letdown time of the year, right, where everything kind of, you're just trying to finish out the year and you take a little lull and stuff like that. So we've only got one show this month, and it's the last one of the year. But forgive us for that. We'll be back in 2014 with better, bigger, more stuff. But in that light, today's show actually features some of our friends that we ran into at Supercomputing. And we have some cool stuff to talk about, right, Brock?
Yeah. So this is
and also we have. I think this is a dubious distinction for this episode. This is the first time our guests have ever attended via iPad, because we record via Skype, but I'm pretty sure we've never had anybody attending on Skype via iPad before. So this is a minor first for the show.
Well, this is how you kind of get around some of those workplace rules, or not really get around. I believe they're also like on a trailer off-site to be able to even make this call. So our guests today are actually Katherine Moore and Adam Moody, both of Lawrence Livermore National Lab, who are going to be talking to us about Scalable Checkpoint Restart. So Katherine, why don't you take a moment to introduce yourself?
Hello, everybody. I'm Katherine Moore, as he said. I'm a researcher at the Livermore National Lab. I work in basically scalable tools for high-performance computing, for example, fault tolerance tools and performance analysis tools.
Adam?
Yeah, so this is Adam Moody, also here at Livermore. I graduated from Ohio State and then started my career out here in 2004, mainly hired to support the computer center with an MPI background. And with that, sort of also got involved with fault tolerance, which is how SCR, or the Scalable Checkpoint Restart Library, came to be.
So I got to say something in here, because I got to point out I'm at the University of Michigan, and I'm very sorry about a certain football game. And I'm sure you're very happy about a certain football game, but most people don't know University of Michigan and Ohio State are rivals.
He has Buckeyes around his neck right now.
He has Buckeyes around his neck right now. I'm virtually punching you in the face.
Brock is sad panda. That is more politically correct right now, I think. Yeah.
Yeah. Okay. But
let me start off the official part of the podcast by, hey, Adam, Katherine, why don't you tell us what Checkpoint Restart is? And let's start off with a simple case, like a single process case. What is kind of the goal of Checkpoint Restart, and what is it?
So the idea of checkpointing is if you have a long-running job that could be interrupted, you occasionally want to save the state of that job so that if it does get interrupted, you can recover from that state. And so the analogy I like to use with people is, imagine that you're working on a Word document or something, you're writing a paper. You occasionally save your work every couple of hours, because in the case that Microsoft crashes, you don't want to have to rewrite that couple of hours worth of work. So maybe every 5 minutes you save whatever work you've done, and then you can restart from that in case you get the blue screen of death.
Now, we don't usually get the blue screen of death in high-performance computing, though. So what kind of reasons do you have for Checkpoint Restart?
Well, yeah, so in HPC, it's sort of the same idea. You don't get the blue screen of death only because we're not running Microsoft, right? But Linux also fails, and the hardware also fails. But the bigger problem is that you're using far more processes. And so typical HPC jobs at a large computer center might be using, say, 1,000, 10,000, 100,000, even 1 million processes at once. And all of those could fail either because of software problems or hardware problems. And these simulations tend to also run for a couple of weeks at a time. And so you're almost guaranteed that something will fail along the way. And so to combat that, people use Checkpoint Restart. Each process saves its state periodically, and then you can restart the job in the case of a failure.
So it seems like a really naive way to do this would just be to serialize everything in RAM and write it to disk. What are some of the problems with doing something like that?
Well, primarily the problems are the high overhead of reading and writing the checkpoints to the parallel file system. And this occurs because when you have a large number of processes in your job and they're all trying to read or write at the same time, the parallel file system becomes a huge bottleneck. And this overhead is a pretty serious problem. For example, for a large-scale job, it could take on the order of 30 or 40 minutes just to write out a checkpoint. And during that time, the entire job is blocked, just waiting for it to finish. And so the machine is not well utilized in that way.
So really, actually, just one clarification point. It's not dependent upon a parallel file system, right? It's writing to any stable storage, right? Just to clarify that.
Well, that's the approach that SCR takes, is writing to any kind of stable storage. But typically, without a library like SCR, the only storage available is the parallel file system.
Okay, so then maybe you could broaden your definition a bit. So I asked Adam specifically about, checkpoint restart in a single process state, and you've kind of alluded that, with these big parallel jobs, there's lots of processes running on. How do you apply checkpoint restart to an HPC job? Just expand that definition a little.
Well, so it turns out at Livermore that we sort of force a failure every so often, just because we timeshare the machine. So applications will run maybe for weeks at a time, but we only give them maybe 12 hours at a time on the machine so that multiple people can make use of the machine at once. So at least every 12 hours, they have to stop the job and then in another 12-hour window pick up where it left off. And so the way people have dealt with that is that each process right now will open a file, write out whatever state it needs to capture, close the file, and then those files are saved on the parallel file system because that's where they can persist the data between runs.
So why go directly to a parallel file system? Why not just use, a lot of times nodes have a local drive, why not do file per process and kind of aggregate them up later?
Well, that is what SCR does, but the problem with doing that naively is that if you lose a compute node, you've lost the checkpoints if they aren't pushed out to some stable storage, or if you don't apply some redundancy schemes, like copy a checkpoint to a different compute node to prevent loss in case of a failure. So that's where SCR comes into play, is it does all this magic for you, and you just have to write your checkpoints like you normally would, but you experience much, much lower overhead.
I see. So one of the issues you're running into might be the actual failure of the node or even the disk itself, not just this 12-hour reset for time-sharing purposes. And so in that case, if you wrote out to the local disk, it's effectively gone and you can't get it. That's what you're saying, right?
Correct, yes.
Now, what other kinds of failures can occur?
Well, so the compute nodes, we call them nodes, right? They're really an individual computer, but because computer has too many syllables, we say node all the time. But a node basically is made up of a motherboard, a processor, some RAM, a network card, and maybe you have a disk on the node or not. So any of those components could fail. The ones that we see most often are the power supply on the motherboard. Network cards are also a common failure. Every now and then we'll see some processor failures or some RAM failures. The other big failure mode, though, is really software.
And the parallel file system.
Oh, right. And yes, the parallel file system also fails, unfortunately.
Now, when you say the software fails, though, I would imagine that it would fail for all processes in the job. Like it's a user error. Are you talking about something else?
Well, I guess each of the different processes is going to be executing with different data. And so one reason might be that there's some instability in the computation and they get a floating point exception or something like that on one of the ranks and not the others.
So what would happen in that case? They would restart from one of the checkpoints taken previously, right?
Right. So the MPI job would abort in that case, and then